All right. Hello, Professor Rudney. This is Gerard, and I just wanted to show you some quick things of what I've learned in this 5-week class. Let me start off with the digestive system. Okay, so first thing are the functions, right? We got peristalsis, chemical, mechanical digestion, ingestion, elimination, absorption, and secretion. Next is the anatomy. So we start at the top. We got the mouth. The most important parts are the mouth, pharynx, esophagus, stomach, small intestine, large intestine, and anus. Some accessory organs or accessory parts would be teeth, tongue, salivary glands, liver, pancreas, gallbladder. Yeah, it's accessory. Next, we go to the functions. So the mouth function would be chewing, swallowing, and beginning the breakdown of carbohydrates and fats. So let's do the salivary glands next. So there are two types of salivary glands, the intrinsic and extrinsic. So the extrinsic produces amylase and intrinsic produces lipase. And the differences is that amylase breaks down carbs, lipase fats. Amylase is 6.7 around that pH, and lipase is 8. This is the optimal pH for them to function. And the inactive would be less than 4.5 and around 6. This is important because in the stomach, amylase is actually inactive because the stomach is too acidic, which you can see in their locations. Amylase is found in the mouth and small intestine, while the lipase is found in the stomach, small intestine, and mouth. Amylase is found in, or is produced by pancreas and extrinsic salivatory glands. Lipase is produced by zygomen, pancreas, and intrinsic salivatory glands. Zygomen are actually found in the stomach, so that makes sense. Alright, let's continue to the math and swallowing, deglutition, the phases. First is voluntary, and involuntary, the tongue squeezes the hard palate, which pushes food to the soft palate. Very easy. Then pharyngeal, which is involuntary actually. When the food hits the soft palate, the nasopharynx contracts, which causes the food to go to the next phase, esophageal. And this is where peristalsis starts. So first, the upper sphincter of the esophageal opens, and this allows food to go down the esophagus to the stomach. Now there's two sphincters of the esophageal, upper and lower. The upper has a partial pressure, or I'm sorry, has a pressure greater than 760, which is greater than the atmosphere. So it stops pressure from coming out. Coming in. The lower sphincter has 10 pressure greater than stomach, which means that stomach stomach substances won't come into the esophagus, which is good. We don't want stomach things in the esophagus. That would be bad. So after the esophagus, we go down to the stomach. At the cardiac, drops into the cardiac and into gastric pits. Now, in the gastric pits, we have secretory cells. We have three types. We got the mucosal, parietal, and zygomen. Mucosal makes bicarbonate, which protects the linings of the stomach. It does this because it is very basic. Oh, looks like Alexa was talking to me. Sorry about that. It's very basic, which protects from the acidity of the stomach, which comes from the parietal. The parietal secretory cells produce HCl and B12, which is intrinsic factor. HCl is acidic, and it activates pepsinogen, which is produced by chief cells or zygomen. And pepsinogen turns into pepsin, and it helps break down peptide bonds. Zygomen also produces lipase, which you can remember from this chart. And there's also G cells, gastrin cells, which help stimulate stomach. Now next are the three phases of the stomach. The cephalic, which is basically when you see or smell food, it causes the parasympathetic system to go to your stomach and release um, gastrin cells, which start um, stimulating the stomach. Next is gastric phase, which is when the stomach distends, when there's food in the stomach. Next would be the intestinal phase, when it's entering the duodenum into the small intestine. And this has three hormones actually, secretin, CCK, and GIP. They help inhibit the stomach. And last we have Brunner glands. They release H bicarbonate to increase pH levels. Now, from the intestinal phase, we go down to the duodenum and to the which is the small intestine. The small intestine has the duodenum, jejunum, and the ileum. Now, some things to remember about the small intestine phase are its hormones. Its hormones include CCK, which doesn't only inhibit the stomach, but it actually stimulates bile and pancreatic production, and secretin, which helps with water flow. And it also has enterocrinin, which also helps with water flow, and most importantly, enterokinase. Enterokinase is really important in turning trypsinogen into trypsin, which I'll talk about in the pancreas. Let me find the paper. Here, the pancreas. So first, the pancreas hormones, CCK and secretin, both inhibit the stomach, but CCK stimulates the pancreas and bile release, and secretin increases water flow and bicarbonate in water. And the most important parts of the pancreatic enzymes are the amylase and lipase, like we talked about earlier, and chymotrypsinogen and trypsinogen. Now, back in the small intestine, enterokinase would activate trypsinogen, which would turn into trypsin, and trypsin activates chymotrypsinogen. But trypsin also activates trypsinogen, so it's just a positive feedback. Some important things to remember is chymotrypsinogen is least specific, most abundant, and trypsinogen is most specific, least abundant. Next is the liver. Liver's function, create bile, and bile's function is to emulsify fats, which means to break down fats into smaller pieces so that the lipase can break it down further. And another function is to lower the optimal pH of lipase to 6. Very important. And remove waste. Now the components, 12.5 parts cholic acids, 2.5 parts phospholipids, 1 part cholesterol. It's mostly water though, mostly water. Now it is 3 to 5 grams of bile used per meal, and in total we have 3.6. And we eliminate about 0.8 grams in our feces, and we make it 0.8 grams in our body, so equals out. Enterohepatic cycle is when it goes from the liver, small intestine, blood, back to the liver, so on. Now, after all that, we have, absorption. All right. Oh, actually, let's talk about the last, would be colon. Colon's pretty easy, just gotta remember the functions. Reabsorb H2O, store undigested food, and eliminate, and don't forget about vitamin B and K. There's this large intestine, goes into the anus, and you know the rest. And then the last part would be absorption. Now, absorption is very interesting. It's the final breakdown of proteins, carbohydrates, and fats, which is used by membrane-bound enzymes. For proteins, it's I think it's aminopeptidase, and for carbohydrates, it'd be very specific to what their name is. Like sucrose would be sucrase, maltose would be maltase. Basically, if it's I think it's a disaccharidase, but you can really easily tell by the ASE at the end of what sounds like a sugar, like sucrase. That means it breaks down sucrose because its ASE is enzyme. Okay, and then next would be lipids, and lipids are very different from the other two. They're actually released back into the liver in the form of micelles. And then in that form, they are broken down by they're broken down by um, lipo um, proteinase. And that is the digestive system. Next, I want to talk about the respiratory system. So let me find it. So next, I just want to do a quick overview on the alveolar exchange. So first, we start off here. This is the chart, and so first we start off here. This is the chart, and this is the alveolar end of exchange. Okay, so majority of the O2 diffusing into the cell would be through oxyhemoglobin, which is 97%. About 2% would be just diffusing to the plasma over here. So O2 goes in this direction. So O2 goes in this direction in the alveolar end, and it binds with a hydrogen ion and a hemoglobin, which turns into oxyhemoglobin plus the hydrogen ion here. And from there, it turns into hemoglobin plus potassium. Now, where the hydrogen ion went is over here, down here, to the which we call the Haldane effect. It actually binds with a bicarbonate, which was just chilling in the plasma. It's about 67% in the plasma near sodium. It's a lot of space, so easy way to put it. So this bicarbonate actually goes in, and the chloride that was here goes out. This is called chloride shift. Now, after these two bond, it's called carbonic acid, and this can be broken down by the carbonic anhydrase, which turns into H2O and CO2, which are easily able to be diffused out of the cell. That's about 67%. Now, this is about 20% of diffusion. This is hemoglobin and CO2. They just dissociate. They just dissociate in the cell, and they also exit. Lastly is when CO2 just dissolves in the plasma, same as this, about 4%, and then out. So that's the alveolar end of exchange. Some other things to remember is, I guess, the pulmonary gas exchange. It's pretty simple, really. So we start off, this is the aorta, is the vein side, veins. This is the arteries, and this is the tissues. I'm writing on a mouse, kind of difficult, but it's fine. I hope you can understand it. Okay, so we start off here with the vein side. So it'd be about CO2 would have 45, I believe. Yeah, 45, and O2 somewhere around 25 to 75. And in the aorta section, it's about 105 oxygen and 40 CO2. So through just passive diffusion, or through just diffusion, 45 goes to a place of lower pressure, so up there, and the oxygen comes from a higher pressure to a lower pressure down here. So the new pressure would be 40 and 105. That's the aorta section. Now this number continues down here, and then it continues into the tissue, and out of the tissue, it becomes this number, 45, 25, 75. And that's the pulmonary gas exchange. Okay, Professor, so that's the end of my lecture. I hope you enjoyed. In summary, we learned about the digestive system, um, pulmonary gas exchange, and the alveolar end of exchange. And that's really it. I hope you enjoyed, and have a great summer.